Hello and welcome to the third lesson in our series on light and lenses. At the end of the last lesson, I asked you to think about what would happen if we moved an object that was beyond 2f closer to the convex lens. Well, I've got a light bench here, so let's find out. The object in this case is a specially shaped light source. Then we have the lens, and on the other side of the lens we have a screen. At the moment, the object is beyond 2f for this lens, and you can clearly see that the image is inverted, smaller, and falls between f and 2f on the other side of the lens. Now let's move the object closer to the lens. The image is still upside down, but as the object gets closer to the lens, the image gets bigger and moves further away from the lens. Now let's see what the image looks like when the object is at exactly twice the focal length, or a distance of 2f from the lens. Remember, this was your task from the last lesson, so you can check your answers against my diagram. As before, we draw in the same two rays from the top of the object. Again, we see the image formed here behind the lens, and you should see that it's a distance of 2f from the lens on the opposite side to the object. The image is also exactly the same size as the object. I hope that from our investigation so far, you can see that the size and position of an image will be determined by the focal length and by the position of the object. For the rest of today's lesson, we'll have a look at what happens if the object moves even closer to the lens, and we'll take a closer look at the idea of magnification. By the end of today's lesson, you should be able to draw a ray diagram to determine the nature, position, and size of the image formed when an object is placed at any position in front of a convex lens, and calculate the magnification of a lens. First, let's summarize what we already know about convex lenses and the images they produce. While you're watching, you could fill in a table like this one to help you collate your observations. If an object is far away from a convex lens, far beyond 2f, a small, inverted and real image forms at or close to the focal point. When an object is in this position, we say that the object is at infinity. See how I have recorded this information in my table. As the object gets closer to the lens, the image gets larger and moves away from the focal point, but it's still smaller than the object, upside down and real. But when the object is at 2f, although still upside down and real, the image is now the same size as the object. Now, I want us to think about what happens when the object moves into the space between 2f and f. Can you make some predictions of what will happen to the image? Let's look at an animated ray diagram and see what happens. Notice as we move the object to between 2f and f, the image is still inverted and real, but this time it's larger than the object. As the object gets closer to the focal point, the image is clearly getting very big, but it's still inverted and real. Can you see a pattern developing in the type of images formed by convex lenses when an object is placed at different positions in front of the lens? Let's look at the table of data to see if we can find the pattern. When an object is placed beyond 2f, the image forms between f and 2f behind the lens and is smaller than the object. When the object is placed at 2f, the image forms at 2f behind the lens and is the same size as the object. When the object is placed between 2f and f, the image forms beyond 2f on the other side of the lens and is enlarged. It seems that the further away the object is from the lens, the closer the image forms to F on the opposite side of the lens. The image is also very small. As the object moves closer to the focal point of the lens, F, the image moves further away but increases in size too. So what do you think will happen to the image when the object is at F? This is really interesting. Look at this ray diagram. The two rays from the top of the object travel parallel to each other after passing through the lens. These lines will never meet, so we can say that an image forms at infinity. This really means we cannot see any image forming here. Now let's move the object closer to the lens, between the lens and F. What image will form now? Why don't you try to draw a ray diagram of this situation? Check out my ray diagram. Here's an arrow representing the object placed between F and the lens. We know that a ray of light from the top of the object that travels parallel to the principal axis gets refracted by the lens and passes through the focal point. Now let's look at the other ray of light that travels from the top of the object through the center of the lens O and carries straight on. Hey, these rays are moving away from each other. This is the opposite of converging and is called diverging. So, where's the image? Check out where the lines come from. By extending the lines backwards in front of the lens, they meet over here. This point now represents the top of the image, and as you can see, the image is going to be upright and enlarged. Because we had to draw the lines backwards, this means that light did not travel to the image or come from the image. So the image is a virtual image. It is not a real image. Notice that to see this virtual image, I need to look at it through the lens. Can you see that this image is very much like the image formed in a mirror? When the object is this close to the converging lens, we call the lens a magnifying glass because it magnifies or enlarges the size of the objects, at the same time keeping the image upright, not upside down. Magnifying glasses are used by stamp collectors. They also help elderly people to read, and biologists use them as simple microscopes to help them see small insects and plants. Take a few moments to fill in these new observations onto your table. This is how I have done it. When the object is at F, no image forms. And when the object is between F and the lens, the image forms behind the object on the same side of the lens, and the image is larger than the object and virtual. Now that we have a very good idea of where images form when we use convex lenses and what the properties of these images are, there's something else I want us to think about. Notice that some of the images formed by a convex lens are enlarged, while other images are diminished. We describe an optical device's ability to produce images that are either bigger or smaller than an object as the device's magnification. I am sure that you will agree that it would be useful to know exactly how much a device will magnify an object before we buy a device, right? Well, we can. The magnification of optical devices can be calculated in different ways, but for now I'm only going to focus on two ways of doing it. The first one is really simple. All we have to do is compare the size of the image to the size of the object. But something very important to remember when you do this calculation is that when we talk about the size of the object, we are not talking about its actual size, but the size we perceive it to be when we look at it with our naked eye. For example, let's think back to the magnification of the rear view mirror in a car. When you look at the car behind you through the back window, it looks to be 1 meter high, but in the mirror it looks to be only 5 centimeters high. Then substituting this into our formula, remember you first convert meters to centimeters, we find that the magnification of the rear view mirror is 0,05. Notice that magnification has no units. As another example, let's consider a scale diagram of an image formed when the object is placed between 2f and f in front of a convex lens. Here the image is 4 centimeters and the object is drawn as 2 centimeters tall. If we substitute into the formula again, we find that the magnification of this lens is 2. Easy! Another way to calculate magnification is to divide the distance that the image is from the lens, we call this V, by the distance that the object is from the lens, we call this U. Let's measure these distances on our scale diagram and see if we come up with the same answer for the magnification. V equals 12 centimeters and U equals 6 centimeters. If we substitute these values into the distance formula for magnification, we once again get an answer of 2. To make sure that you have a very clear understanding of what we have learned today, try today's task as practice. An object that is 20 millimeters high is placed 25 millimeters away from a convex lens with a focal length of 30 millimeters. Draw a ray diagram using a scale of 2:1 to show where the image is formed. Calculate the magnification of the lens using either the equation m equals image size divided by object size or m equals image distance divided by object distance. I am sure you'll have fun with this task. I'll see you again next time when we look at the images formed in this kind of lens.